As a first method, we will discuss the direct method of proving. It's basically the most simple and straightforward proof technique. This technique aims at proving statements of the form if P then Q, or alternatively we can write if P implies Q, which can be written in this form here, P arrow Q. So let's assume we want to show such a statement of the form P implies Q. The proof steps are actually pretty straightforward. We simply assume the statement P would be true. And then we use what we know about P and other facts about a background theory, like for example, if we talk about numbers, then we talk about the mathematical knowledge about numbers, which we can use. So we use these other facts as well, and then we deduce that a statement Q is true. And with that, we basically did show if we assume P is true, then Q is true, and hence we have shown P implies Q. Let's make an example. So let m be an integer. If m is odd, then m square is odd. So here you have exactly this implication written in text. If m is odd, then m square is odd. How does the proof work? Well, if m is odd, then from mathematical theory, we know that we can write it in the form m equals 2 times r plus 1. So it's an even number plus 1 for some unknown integer r. We can then use this to rewrite it into the form m square. We replace it here by 2 times r plus 1. We then transform it using our background knowledge about mathematical theory and come up with this formulation, which again shows this is an odd number. Thus, we can conclude m square is odd. A variant of this are so-called if and only if proofs. This means basically two statements are equivalent. The way we typically address this is we take it apart into two different subpieces, one for each direction. So we basically prove an if part in one direction and only if part in the other direction. So we basically show for A if B that B logically implies A, and for A only if B that not B logically implies not A. Meaning if we negate B, then we can imply that A is also not true. Or this would be equivalent to proving that A logically implies B. So these last two pieces or last two options, they are logically equivalent, and you only have to prove one of those. But you have to prove this one here, B logically implies A, and then either A logically implies B or not B logically implies not A. Now let's do an example for an if and only if proof. Let A be an arbitrary integer. So our example is A is not evenly divisible by 3 if and only if A square minus 1 is evenly divisible by 3. So in that case, we take it apart, as shown here in below. The proof consists of the two directions, the if direction and the only if direction. The if direction would be A is not evenly divisible by 3 if A square minus 1 is evenly divisible by 3, or we can just switch the two parts to bring the if to the front. If A square minus 1 is evenly divisible by 3, A is not evenly divisible by 3. So how do we prove that in a direct way? We know that A square minus 1 can be rewritten as a plus 1 times a minus 1. 3 is a prime number, so we know it has to divide one of those. So either a plus 1 is divisible by 3 or a minus 1 is divisible by 3. No matter which one of those it is, if they are divisible by 3, actually a cannot be divisible by 3. The only if part can be similarly done. So we write, if a is not evenly divisible by 3, then a square minus 1 is evenly divisible by 3. So if a is not evenly divisible by 3, we can write it still in the form a is 3 times q plus r. That actually holds for any kind of number with r is 0, 1, or 2. But because we said a is not divisible by 3, we can actually rule out that r equals 0. So we only have the two cases, r equals 1 or r equals 2. If r equals 1, then a minus 1 is 3q, and so 3 evenly divides a square minus 1. Alternatively, we can make a similar argument with r equals 2. And in each case, because of the multiplication, then actually 3 is evenly dividing a square minus 1. So that's basically how this works. An extension of the direct method, or actually it is an extension of any proof method, because we can combine it with those, is that sometimes it's useful to distinguish different cases. So we do not try to do the proof in a single go, but actually we pick it apart and say we have different cases with different assumptions. Actually, in some sense, you just saw that with the bidirectional proof, where we took it apart into the one direction case and the other direction case. So that's actually a specific variant of proof by cases. So the way it's basically working is that we break a problem down into multiple cases. We do that exhaustively. That's very important. You have to basically identify all possible cases. If you forget one, your proof is incorrect, obviously. So, and then we make a proof for each case individually. Again, for the individual proofs, we can then use any arbitrary method. So that could again be a proof by cases. It could be a proof by contradiction. It could be a direct proof, an induction proof, whatever. So let's take an example and say we try to prove that for every real number x is smaller or equal than the absolute value of x. There are two cases: x is smaller than 0 or x is larger or equal to 0. Let's take the second case first. So we have x is larger or equal to 0. If that is the case, then the absolute value of x is x, because that is already larger than 0. And in that case, we actually have that this holds because x is equal to x, and therefore it's equal or larger than x. The second case is a bit more interesting. Here we have x is smaller than 0. If that's the case, then we have the absolute value of x equals minus x, which is then larger than 0. A positive number minus x is always greater than any negative number. Thus we know that this minus x equals the absolute value, which in turn is larger than x. And thus we can conclude that x is smaller or equal the absolute value of x. In both cases, we get the same formula. We have a complete decomposition because there's no other way or no other possibility for x. Therefore, we have exhausted the different possibilities, and that is also the reason why this method of proof by cases sometimes is also known as exhaustion. So next, let's do a small exercise. We use a rather simple example. So let's say we want to show that a program of the form given here on the slide will always increase the value of x if the value of x prior to its execution is larger than 0. Just as a word of explanation, this percentage sign is a modulo function or remainder of an integer division, meaning if I divide an integer number, then of course I cannot get a fractional result if I use integer operations. So if, for example, I divide 7 by 2, then I get 3. But there is a remainder, and that is actually what this function is giving me. So if I do the remainder versus 2, then the remainder can only have the two values, 0 or 1. So that's what's happening here. So this actually means that this would be an odd number. Okay, with that background knowledge, this is to be proven by decomposing it into two cases, applying the direct method for each of them. Also, as a hint towards the notation, so you can write this down rather easily, is use x to denote the value prior to execution and x prime to denote the value after execution, so you can have mathematically the relation between two. With that, stop the video and give it a try for yourself, and only afterwards resume. Okay, welcome back. As a piece of reference in the upper right corner, you have the program. Now, let's say we do as first case, case A, x modulo 2 equals 1. So we need to show that x larger than 0 leads or implies to x prime larger than x, meaning the value of x after execution is larger than the value of x prior to execution. So in this case, if it's an odd number, then actually this statement gets executed, x equals x plus 1. So if we use the mathematical notation and use x prime for the value afterwards, that means x prime equals x plus 1. Thus, actually x prime is really larger than x. So for the second case, B, then it's an even number, meaning the remainder is 0. We also need to show that x larger than 0 implies that x prime is larger than x. In this case, we actually have the second statement, x equals 2 times x. But we can again use our notation and use x prime, then x prime equals 2 times x. Thus, because we initially assumed that x is larger than 0, we can actually rewrite that as x prime is 2 times x, and that is actually x plus x, and x is something larger than 0, so that means 2 times x is larger than x. And with that we get x prime is larger than x. So for both cases, we now have shown that the relationship we were seeking holds, so we can make this conclusion.